And I would like to welcome you all to this webinar that will be focused on digitalization of injection molding lines for repurposing. So I prepared some slides just for introduction. So you can see here. As said, this is the third webinar of a series, and imPURE is organized in 4 main pillars. The first is the production, concerning the repurposing of industrial injection molding lines. The second pillar is dedicated to flexibility with additive manufacturing for the preparation of molds. Third pillar dedicated to automation, sensor, machine learning. And the last one is dedicated to operators, so our end users, which will deal with digital twins for training. So we have organized, as anticipated, already 2 webinars. The first, which was dedicated to product design and development for imPURE's critical medical supplies, held on the 27th of October. The second, dedicated to fast-track modular mold development and metal additive manufacturing for injection molding molds manufacturing, held on the 2nd of February this year. We have the third webinar organized today, as said, dedicated to the digitalization of injection molding lines for repurposing. And the fourth one will be organized at the end of May, when the project will reach its end, so the 25th of May, and it will be dedicated to the supply chain collaboration platform and distribution of critical medical supplies. So the webinars are mainly representing the overall imPURE activities and the TRL transitions. You can see here a screen where the main activities are highlighted and which is the flow that the activities are following. We start from a TRL 6, 7 by ending to TRL 8. You see here the major activities carried on, starting from the raw material supplies dedicated to metal powder and antimicrobial polymer buster batch, and then we will end with our 4 case studies repurposed. So you will find in the last webinar also how they have been developed and how they will be transported. So we will make some presentation also on how we ensure its collaboration with end users and the construction of the platform, as well as the flow of digitalization and distribution. So the webinar today is dedicated to the digitalization. As said, we will hear several presentations from our main partners dedicated to the topic, starting from Jules Verne with the presentation on injection molding process monitoring. Hi, good morning. The second presentation will be given by NIT on introduction to the thermography applied to IM lines. The third from Innova on physically based digital twins for injection molding. The third from IES on cloud data management and visualization for remote manufacturing. And the last from IRES on defect detection using synthetic data and exploration of real-time IM cycle data. So the webinar today will be mainly focused, as already said, on digitalization. We have several external stakeholders registered. You can see here a list, and the main topics developed and basically repurposed are measurement technology, industrial process control, sensor technology, data acquisition, signal conditioning system, piezo technology, test and measurement, process monitoring, and sensors. So we have an overall perspective on who is with us today, which we thank you again to join us. And then, of course, we will have a Q&A session in case any of you would like to raise some questions to our speakers on the topics that will be presented in few minutes. So this is my contact in case you would like to reach out, and in case you would like to have any additional information on the webinars that I have already organized, or on the next one that will be organized at the end of May. So thank you again for being here with us today, and I would like now to give the floor to our first speaker, Philippe Lebeau from Jules Verne, which will give us a presentation on injection molding process monitoring, principal components analysis. So, Philippe, the floor is yours. If you'd like to start sharing your presentation.
Yes, thanks a lot, Stefania. Do you see my screen? Is it okay?
Yes, we can see properly.
Okay, thanks a lot. Thanks a lot. So I'm pleased to bring you some elements of understanding concerning the monitoring of a thermoplastic injection process applied to a medical part. The imPURE project, as you said just before, is a European project which, in the context of COVID-type health emergency, consists of repositioning automobile product lines into medical production lines. And the main idea of this seminar is to present different elements, you can see there, different elements to ensure an acceptable final quality on the part in a minimum of time. So we present, the different speakers will present different steps, different points of view, different technologies, which complement each other to achieve this goal. On behalf of Jules Verne Institute, which I represent here, I'm going to present to you in a few minutes an approach to descriptive monitoring of the injection process using exogenous instrumentation and a mathematical approach based on principal component analysis. My partners, the other industrial partners, will present then other approaches. To begin with, just a view of injection molding. The injection molding process consists of injecting a thermoplastic resin into the cavities of a mold. This resin, which is brought in granular form, is melted in a screw and barrel assembly system. This is the plasticizing phase. It's then injected under a controlled speed of screw into the tool, which is cooled by fluid channel. This is the filling stage. When the cavity is filled, the hydraulic pressure required increases very quickly. To avoid an involuntary opening of the mold, the control mold switches to a forced hydraulic pressure. This is the packing phase. The point of transition between the filling and the packing is called the switchover point. It's a quite important point for setup for operators. At the end, the cooling phase without any pressure is applied before the mold is opened and the part ejected. To monitor the process, it's often necessary to add sensors to the mold. Although traditionally, hydraulic pressure and screw position sensors are used to analyze the cycles. There are many different sensors you can see on this table found in the literature, able to measure physical quantity, pressure, temperature, and many others. You can see on this slide some commercial sensors. Here, an infrared sensor from MTS. Here, a piezoelectric sensor from Kistler. Here, an electric sensor from TFX. There are also some academic sensors. Here you can see a wireless ultrasonic sensor from Kazmer team from US. All these sensors have the ultimate aim of helping to control the process, ensure good reproducibility, detect anomalies, improve the process, and optimize the setting. To illustrate the possibilities of using these sensors, you can see here 4 examples found in the literature. On this one, the first one here, it consists of placing a pressure sensor at the end of a filling and using it as a material from detector to trigger the switchover point instead of screw position. You can see for the same production here, a comparison concerning the stability of process if a switch over point is done by screw position or by pressure sensor. A second, like that. The second example concerns the control of the injection process with the help of sensor into the tool. The pressure sensor here can be used to adjust not only the switchover point, but also the packing phase steps to avoid overpacking effect. The third example here is the monitoring itself of the process, illustrated here by a screenshot of the system Comoneo from Kistler. This involves monitoring whether the pressure curve over time remains the same from one cycle to the next. Finally, here, TFX has shown that by judiciously placing a head flow sensor in the cavity, they are able to detect shortcuts. I have a yes. There are a number of data acquisition systems in the industry dedicated really to injection molding process. This list is not exhaustive, nor it's a preference. Kistler from Comoneo, no, Comoneo from Kistler, sorry, QDAC from Primus, HIDA from RGJ, SMC from Cavity High. These systems use pressure and temperature sensor data with a process expertise approach close to the operator's experience and monitoring by classical statistic process control method. These tools are efficient and allow the detection of most of the anomalies. Two additional commercial tools allow a principal component analysis approach. You can see here PSP from SEAS and Sensiling from MKS. One of the objectives of process monitoring is to detect any anomaly during the cycle in order to avoid scraps or non-quality costs on the final part. If we plot all the cycles in the same graph for machine or mold parameters over time, we can realize that the cycles, so the parts, are similar but not identical. Among potential causes, classically, operators particularly monitor the cushion and the switchover points. Now, the SPC method consists of monitoring parameters one by one, independently of each other. If your measure value falls outside of an interval from statistic or expertise, an alarm is issued for suspected process drift or non-conforming parts. Now, if we consider two parameters, this one and this one, for instance, linked each other here, we can see that for the example of the red part, the red point here, that the part seems to be in conformity for each one. But if we consider the two parameters at the same time, this red part does not seem to be in conformity. A change of reference point made back, or a change of reference point then makes it possible to consider a new variable here, a linear combination of initial parameters, and which seems more relevant to describe the process. Now, imagine not two parameters, but 200 or 2000 parameters, with some links not known a priori. This method must be then made mathematically without any a priori knowledge of the connections between the variables. This is the principal component analysis approach. A calculation of eigenvalues and eigenvectors is the ideal solution. To do this, several calculation steps must be done. The first step is to summarize time series data into parameters by expertise approach. Then we make the variables dimensionless. A transformation into reduced centered variables is ideal. Missing data and outliers are then dealt with. Do not forget to analyze the correlation matrix between variables studied in order to compare it with the experience of the operators and the process expertise. At this point, the points, the parts, can be projected onto the eigenaxis, as was done here on this simple example. Now, I will try to show you in the following two examples the interest of this monitoring methodology. The first example is come from a laboratory part, which enabled us to test the method. The second one is a validation of the method on one of the medical parts studied in the imPURE project. Let's go to the first one. So for the first one, we went to a laboratory at TEN in Nantes with the staff of the company capacity to help us to do the experiments. Thanks for them. This part is an injected plate of a 3 mm thickness and 60 mm side in ABS. The mold is equipped with pressure and efflux sensors. A TFX data acquisition allows to store the screw position and hydraulic pressure signals from Sandreto machine, as well as the pressure sensors and 3 thermocouples in the tooling, in the mold. Production was made like that, a reference production, a 10-minute stop, and then after a new production of 60 parts. Okay? After a new 3-minute stop, a voluntary anomaly was introduced. The heating of one zone of a screw was stopped, was switched off. At the end, a drastic decrease of the heating of all of the zone of the screw was done, was shutting off. After 34 parts, a short was detected on the part, and we measure part weight. The challenge is to know if a monitoring method with principal component analysis will be able to detect this anomaly before the short appears. The first step is to analyze and interpret the signals from the available sensors. The idea is to understand the process through these signals. Here we can see the interpretation that can be made from these signals, the division into some several stages: filling, packing with a switchover point detection, plasticizing, decompression after plasticizing. And the meaning of each detail, you can here see the focus on one of them here. The passage of material at the gate, solidification of materials, shrinkage, back pressure, and so on and so on. This step allows each of these curves to be summarized into a certain number of representative parameters. Simple tools are used, such as maximum, minimum, integral, derivatives, etc. The information provided by each of these sensors is then reduced to a set of parameters. Here you can see 8 of them. In that case, we detect 50. You can see some example of them, okay? Now, the principal component analysis from these parameters, the 50 parameters, gives this type of results. You can see the projection of each point. One point is one part. On the eigen axis here, axis 1 versus axis 2. Parts for which a process defect has been deliberately introduced can be detected quickly. It's the orange points there. In one single screen, potential anomalies can be detected. On the top of that, different parts can be seen, especially at the beginning of a production or the restarting of a new production. The first one and then the following one before stabilization. This is due to the establishment here, the establishment of a pseudo-established thermal regime. visible on the tooling temperature parameters, such as this one. You can see the augmentation of mold temperature at the top injection, for instance. So in one slide, in one screen, you can summarize 50 parameters together. What happens now if we go to industrial scale? The aim here is to analyze a two-cavity molding system for making oximeter. You can see here the two cavities there. The University of Strathclyde in Glasgow was responsible for installing sensors around this production at Pasquay, thanks to the Pasquay team and thanks to Strathclyde team, Manaf and Bert. So we install sensors, screw position, you can see here, screw position, hydraulic pressure, but also pressure and temperature sensors in each cavity. A Kistler Comoneo system was installed with the help of Kistler, who provided invaluable assistance. Thanks a lot, Kistler. The Comoneo system is connected by OPC UA protocol to the Synapse system, which is a system developed by Jules Verne Institute, which allows principal component analysis online, on real time. This OPC UA protocol allows the transfer of data in an industrial and secure manner. The same methodology is applied. We study the evolution over time of each signal, of each sensor, and we try to understand each curve. You can see here the first part of the analysis from which we can extract the different stages: filling, packing, cooling, plasticizing. Not that the curves are not similar than the previous one, totally different, but it does not alter the method, which remains the same. The production was carried out as follows. First production phase with apparently a cooling problem occurred. You can see here something very strange there. A reference production and the last production identical, but after a 10-minute stop. We note that there are not many differences between the two cavities, so we can here, for the understanding of the presentation, consider only one cavity instead of the two. The methodology remains the same. The curves are summarized by representative parameters. Here, 62 parameters have been calculated. We can see some by these parameters that 5 cycles here seems different. This one. It can also be seen that 50 cycles could be detected as different, but it's not very obvious on these parameters. Now, when considering these variables of the analysis and projecting the cycles onto the eigenaxis 1 versus 2, it can see that the 5 parts here appear very clearly outside the point cloud. If we analyze the correlation cycle, which is the projection of variable into the same axis, we can see that it's due to a set of parameters, this one, which are this one, and this one, connected to the packing time. The process parameters have probably changed during some cycles. It's possible that the operator wanted to test a change of setting during production and then return back to the initial setting. When checked, the change was not significant, but the method of monitoring detected, revealed it immediately. Once again, the effect of tooling temperature can be seen. You can see the first part, and then after the heating of the part during along this direction. Finally, we note that the cloud of a reference part, you can see there, is close to the other parts, even if the first cycles are significantly spotted. This one. Now, we have taken the analysis to a step further by separating the principal component analysis of the parameters related only to the machine settings, those related only to the machine response, and those related only to the cavities. So you can see different results, and this makes it possible to clearly differentiate the effect of a setting from those to the health of the machine and those to the tooling, to the mold, such as its regime, heat transfer regime, but also material effect. It can be here that it can be seen here that the effect of the setting are quickly observable here, and the point cloud, the blue here, remains the same even though it's slightly scattered. At the end, this separation into three distant analyses probably is the most promising for the future. So for the monitoring strategy, we think that the best way is to have three screens from the setting, for the machine health, and for the mold. Now, the last slide. This video, I can launch it, is finally representative of a real-time analysis. On the left, you can see the parameters from the curves. We have chosen to show here only 4 per screen, just for visualization reason, even if behind several tens are accessible. On the right, the principal component analysis is shown. The ellipse here represents the confidence interval of a reference production. If the point of the part is within the ellipse, the cycle is, let's say, compliant. If not, the part is considered, let's say, doubtful. This is the end of my presentation. If you have any question, I think it's at the end of the webinar. Don't hesitate.
Thank you very much, Philippe, for this very informative presentation. I also wrote in the chat that for any question, the participants can write them directly in the chat box, and then we will discuss it in the Q&A session. Thank you very much.
Okay.
Thank you. So I would like now to give the floor to Sergio de la Fuente Leon from New Infrared Technologies, which will give us a presentation on thermography applied to IM lines. So Sergio, the floor is yours if you would like to start sharing your presentation.
Yes, Stephanie. I'm going to do an introduction to thermography applied to injection molding lines. First, sorry, I'm gonna share my window first. Okay, can you see it now?
Yes, we can see it.
Okay, perfect. First of all, sensors have been used on the factory automatization from a whole part now, but the incrementation of boosting power, new technologies, and the increment of the performance of cost to ratio of imaging sensors now allow for artificial vision methods to be implemented on new and already existing factories and process lines. So most sensors most imaging sensors have some key parameters that you have to take in consideration when choosing one, such as the sensitivity, the resolution, time of response, what optics and field of view you are going to need for the processes. Which focus can you apply for the process you are using, and also which temperatures are currently on the process line that can affect the electronics of these sensors. But the key focus, the key parameter that you have to take in consideration here when choosing which sensor which imaging sensor to use is the sensitivity. The sensitivity on the spectral band goes from visible spectral band cameras to several other bands. In this case, I'm going to talk about the infrared spectral band. The infrared spectral band can be subdivided in mostly three bands, depending on the wavelength of the in which the sensor is responsible, is detecting some signal. In this case, the long wave infrared band is the most common and the one that people mostly think when they think about infrared is the one that detects low temperature measurements that goes from -50 degrees Celsius to 900 or even more. This is the cameras that can detect, for example, the body temperature of a person. So those are the most common used ones. You also have the band near infrared, is close to the visible light on the wavelength, and it's used to measure eye temperatures ranging from 450 degrees to a lot to 200 to 2,450, for example. There's also the medium wave infrared band. It's one that allows for the measurement of from low to intermediate infrared to low from low to medium temperatures. These sensors are usually quite expensive because they are refrigerated. Here and there are some exceptions there, such as the lead selenide sensors that we made that don't need to be refrigerated for the use, so they're a bit more cheap in that sense and a bit more affordable. In the case of plastic injection processes, the temperature range is usually from 60 to 180 degrees Celsius. And the emissivity of plastic is usually around, the more typical is 0.9, the emissivity. So you can see a radiance graph here in this presentation, in which will be the radiance of the plastic in these processes. As you can see, from 8 to 40 microns that are that is the long infrared, the long wavelength infrared sensors are the most responsible for, are the most sensitive in this graph. Will be the choice for these processes as they get more signal from the process. These sensors are affordable, are reliable, and are compliant with the industrial requirements for the process, for the most common industrial requirements for the process. So these sensors will be the ones that we will use in injection molding of plastics. Some some advantages of the infrared thermography is that it's a non-invasive and non-destructive process. So it's you don't need to break the mold, to break the product for an analysis. They are very specific. As you get an image of temperatures, you can choose which part of the image you want to measure, which zone, which point, or even several points, several zones. If you see if the operator sees the need to do so. It's also a fast method because you acquire the images in real time. So seeing a change on temperature from an anomalous change of temperature from a mold or so from some elements that you are being producing is fast and easy to see for even non very experienced operators. And because of all these advantages, the analysis of the data can be done without stopping the machinery or stopping the processes, the production processes. It can do real-time analysis of the data without many complications for the production line. Temperature is directly correlated with the defects or the quality of products, both in process like injection molding or in 3D printing applications. So being able to record these temperatures in an image with an imaging sensor like the ones that I'm talking today. Gives a huge advantage for the operator or for the user to analyze the processes or to detect defects on the elements being produced. The thermal images can be used to inspect the machinery, the molding, and to see anomalous changes of temperature there. And also can be an excellent method to automatize these processes. It gives a lot of flexibility and can be implemented in almost every process that can be done. The infrared technique gives some K parameters of the process, such as the deviation of temperature, the detection of hot spots on an image, on a temperature image of a piece or of a machinery, and the appropriate distribution of heat all around a piece. So you can see that there's no concentration of heat and some unwanted part of the piece or of the machinery. You can also, with imaging sensors, you can also measure the cooling process of the elements that you are producing, and you can record data to do some post-processing of this data and validate simulations or validate control process that have been implemented on the production line. Thermal imaging sensors also have the advantage that you can get temperature maps, and these temperature maps are directly correlated with, as I said earlier, as temperature is directly correlated with defects on some elements. Here, looking at a temperature map, you can easily detect these defects. Also, when taking thermal images from a piece after opening the mold, you can you can detect the temperature at which that element have been made. And you can compare these images, one with, from the pieces with another other elements, other pieces that have been made correctly. And using, for example, differentiation maps like the one that you can see in this presentation, you can easily detect the differences between both pieces. So you can detect if a heat, an accumulation of heat, or on some part, or if a colder part of the piece is being seen, can be seen. So you can easily detect the differences between both pieces. Thermography images also, as they give you the wall image of temperature of everything, allows for the user, or for the operator of the system, gives him more flexibility and more options at the time of doing some analysis. You can set points. You can set points to take several measurements or zones. And if you see, if you want to do more analysis on other parts of the image, you don't need to add more sensors. You can just add more measurements on the same image, just giving more flexibility, and not the need of putting more sensors on the product line. Also, having images give more flexibility in the sense of it's easy to see if accumulation of heat, or if a piece, or a metal piece that should be getting hotter is not getting hotter. So you can easily see differences of temperature or anomalies in the image. So this allows for a quick analysis of these parameters, and the appropriate allows the user to take appropriate responses on appropriate time. Here you can see the diagram of process control with a closed loop. In this case, in this diagram, the user will set some points for the software to analyze, the points that are the desired ones. And after the production of the element, when the part is demolded, the measurement of temperature can be done. And this data, it goes back to the software for an analysis, for a comparative analysis with the set points, with the points set by the operator of a correct process. And if these parameters are off from the limits of those set points, the software could correct in real time, could send the request for the temperature control system, for example, to change some parameters to allow for the correction of these problems. There are a lot of imaging thermal sensors, more with each year that passes. There is a technology that is growing very fast, and the affordability and the reliability of these sensors have been higher with each passing year. There are a lot of sensors ranging from very high and very expensive sensors to very low end, more affordable sensors. We at NIT have recently developed this sensor, the Lear 320. It's a sensor with a pixel pitch of 12 micrometers and a resolution of 320 to 240 pixels. It's an easy to use camera with a quick installation and a friendly interface software for the user, so it's very easy to use, and also have some have industrial connectivity, and it's a very small system, so it can be fit in many machines that where the size is a restricting factor. It's also very affordable for its range of capabilities, and it's a good sensor in which we are working for processes like, for example, the plastic injection. Thank you for your attention. That was my presentation. If you have some questions, I will be glad to answer them after when the meeting is finished.
Thank you very much, Sergio, for this very interesting presentation. So thank you very much. I would like now to give the floor to Manuel Las Palas from Itainova, who will give us a presentation on physically based digital twins for injection molding. So Manuel, the floor is yours.
Thank you, Stefania.
Thank you.
Okay, so this presentation is for physical based digital twins for injection molding. And in the flowchart we have shown in previous presentation, this corresponds to a different approach that makes the basis of its analysis on simulations that take into account the physics of the problem. So this part is complementary to the other approaches that we are seeing today that are based on the real data captured by sensors. What I'm going to describe is the process to build a digital twin based on this simulation base that take into account the physics of the problem of the process. So first thing is you need a simulation model that reproduces what is happening to the material in the transformation process during injection molding. Next, what we are going to do is exploiting this model to analyze processing windows of all the input parameters that we have freedom to change in the machine. Based on that data, what we are going to do is to make a results treatment that is called reduce order modeling in order to capture the relevant aspects, the relevant results, and the dependencies with the input parameters. Next step is to put this in a suitable mathematical form in order to be quick in terms of evaluation time. So what we want to do is to be able to have results, to have predictions in real time. And this has two applications. First one, and main one, is to be used as a digital twin for trial and error in a virtual environment without making trials in the real machine. So you can try, you can learn, and how the process behaves, what are the dependencies, and then you can select the trials to be performed in the real world. Second way of using this is making a connection with the real data that the machine is capturing. So if we have a mathematical form that is able to predict some quality performance indicators based on the input parameters. We can link with the sensor readings in order to perform evaluations on the quality of the part produced by the real process. So I'm going to explain a little bit in detail these steps. As I mentioned, the first step is the physically based simulation model. In this case, for injection molding, what we have behind the process is that there's a molten plastic that is flowing through the cavity, through the runners to fill the mold. This plastic is complex, has a non-Newtonian behavior. That means that it's quite affected by temperature, by shear rate, and so on. There is everything is dominated or highly affected by the heat transfer mechanism inside the mold. There is a lot of conduction inside the walls, inside the metallic parts. There is also some conduction inside the plastic, interfaces between the plastic and the mold. There is some convection mechanisms associated with the cooling channels, and also there is obviously some losses of heat on the external walls of the mold. So additionally, for the plastic is a material that is molten at the beginning, and in the end it ends as a solid plastic. So there is a change of the phase of this material, and there is all the process, all the movement of the parts of the volume changes typically originate residual stresses inside the plastic of different origins: thermal, flow, orientation in the case of fiber reinforced plastics, and that orientation and that residual stresses in the end, what they provoke is to that the part distorts, warps, shrinks in a way that changes the dimensions of the parts. So what the process simulation cover is all the phases that are relevant for this process, mainly the filling of the cavity, the packing of the material inside the cavity, how the material is cooled inside the mold and after the molding, and all of these processes, as I mentioned, generate residual stresses, and this allows to perform an analysis of the shrinkage and warpage to try predicting final dimensions of the parts. So the basic process, the first step is you need to decide which are the input parameters you are going to use to create the digital twin. Mainly, they are coincident with the process settings in the real machines. Melt temperature, mold temperature, injection time, the switchover point, the packing pressure, packing time, cooling time. These parameters are the ones that we are going to change in the simulation model in order to have results. Here we have typical results we can get with this type of simulations. These type of simulations are used mainly in the design phase of the molds to get a proper to analyze the feasibility of the process. For example, here we are seeing the melt flow advancement, how the material fills the cavity. We have access to other variables, interesting variables to analyze the process, like the pressure distributions, the maximum pressure that we need to inject the part, or the temperature distributions in the process to see if it's uniform or not. We can analyze how the material is freezing, in which time, how long does it take it to reach the ejection temperature for the material. So we have a very wide quantity of results available of this type of simulations. But the next step, this is one important thing to remark, is that this type of simulations take a while. So if you want to make a combination of parameters and running a simulation, it takes some hours to get the results. So this is something that you can do before you are in production. You cannot you cannot use this type of simulations for real-time estimations. So what we do is exploit the model before. So we generate a DOE, a design of experiments, when we analyze the variables we choose in suitable ranges. These ranges are typically coincident with the processing recommendations for the material and the capabilities of the machine. Next step is, well, here you see a table of simulations run, combinations of different parameters that we run. And next step is to define which are the key performance indicator interesting for the part in particular. This part in particular that we are showing here is the oximeter part in Pascoe line in this imPURE project. And here what we have selected is several critical dimensions or flatness in particular areas, in addition to variables that are overall of the process, like the cycle time, the pressure of the clamp force required for perform this injection. Once we have these simulations done, we can extract the results from the simulations, and we can perform some initial analysis on the data. For example, we can see scattering plots where you can see the range of variation for the process conditions. We have chosen some ranges, and this provokes some changes, some ranges of variations of the different variables we have chosen, like the width or the length of the part or the weight. So we also can analyze here the correlation, which is the correlation that we can see between the inputs in the machine and the outputs in the part quality, to see in a very quick look which are the variables more affecting to particular results. But this is only qualitative analysis. The next step is to convert these predictions into continuum models. What means a continuum model? A continuum model is a model that can be evaluated for any particular combination of process parameters. It doesn't matter if you have not simulated before that combination. It allows you to make a prediction based on the data you have generated previously. So for doing that, there is a lot different techniques. We are using combination of different approaches to perform this continuum model. Depending on the result, we use one or the other, like regression, RBF, surface response, even machine learning models we use for converting this data on models, continuum models. Next is, well, in our particular approach, we convert the models into a single common description and single, that is a very simple mathematical form. That is, we could summarize as a multidimensional interpolation of different graphs that have the dependencies, and the evaluation is just making this interpolation and very simple mathematical expression that has only sums and products. Next is to put this to make usable by the user. So what we have here is an interface that allows us to perform quick estimations, and perhaps this is better if we show on live how it works. So we have the possibility to select whatever result we have previously defined, for example, the length. And we have here the scrolls for the injection parameters. So if we change a scroll, immediately we are having a prediction of the results. What we have here is quite interesting because these are the dependencies, the trend graphs. So for this particular variable, we can see that there is some parameters that are affecting very few, but other parameters are affecting in more or less in an equivalent way. So if we want to, for example, to increase the length of the oximeter, the proper variable would be to working were increasing the packing pressure or reducing the cooling temperatures. But for other variables, for example, the width, these relations can be different. Even the trends could be different. That means that's why this is a valuable tool, because the dependencies are not obvious, and when you have to estimate quantitatively, it's interesting to have a tool such as this one, that you can perform your virtual trials in real time before going to the real trials on the machine. Okay, so we have also some flags here in terms of tolerances defined for all the variables. In any case, we have a variable that gets out tolerance. We will have some red flags. So more or less, this is the tool. Coming back to the presentation, there is a second use of these digital twins. As I mentioned, there is a mathematical expression that is quite simple for each variable that we have chosen. We can use in a different way. For example, instead of making manual evaluations, we can try to connect to the line sensors. If we have records of the process parameters that has some fluctuations and normal fluctuations, and perhaps some anomalies in the process, we can use this as input for the digital twin in order to get an estimation of the quality of the part. Of course, it's an estimation, it's not measured, and it's based on the physical simulations we have performed before. So, but this is useful in some cases, as many times it's not possible to measure all the parts, and it's good to know an anomaly, how it can affect the part quality. So how this is implemented, well, I think next presentation would be more details, but in the end, there is a platform that collects the data and where we can connect through an application program interface to our server where the models are located, and then we can get the data from there, and then we can perform the estimations and provide these outputs to the platform in order to take the decisions based on that. So more or less, this is the presentation. The conclusions I have separated in both types of digital twins. The first is for tryout. As I mentioned, it can be is something that, the advantage is that you can prepare in advance to support the tool setup, initial setup. So you are building the simulations when the mold is being manufactured. It allows a better knowledge of the process because you can analyze the trends and to fully understand the mean dependencies in a quantitative way. That is important. You can perform virtual trials, and also it's important, I have not shown, but this can be integrated in optimization engines. So you can put targets for the different variables and to put an optimization engine to work to find an optimal solution. In the second case, for the quality monitoring, perhaps the complementary approach of this simulation-based digital twin is that allow us to translate input fluctuations and anomalies into part quality estimations. Sometimes you don't know which is the effect of an anomaly. This can give you a way to translate this anomaly into a part quality estimation. If the anomaly is something that can be related to process parameters changes, as this is the basis of our simulation models. Other interesting result is that we have freedom to choose which are the interesting results. So we can define dimensions, we can define temperatures, we can define pressures in different points. So we can include any sensor in a virtual way. That's why it's called virtual sensors. There is not limitation in that sense. And it's complementary to other approaches like data-driven models, as we have seen and we will see later in other presentations. For example, the data from the simulation can be used for initial training of the machine learning models before the real data is available. Or it can be also used for give interpretation to the detections that has been based on the data. You can try to interpret the source by analyzing the dependencies of the variations with the quality results by means of these models. So that's the end. Thank you very much for your attention, and happy to answer any question at the end of the webinar.
Thank you very much, Manuel, for this very interesting presentation. So again, for the participants, you can write in the chat the questions and then we will discuss them at the end. I would like now to give the floor to Giulia Barbano from Integrated Environmental Solutions. She will give us a presentation on cloud data management and visualization for remote manufacturing. Giulia, the floor is yours.
Thank you, Stefania. Can you see my full screen?
Yes, yes.
Great, thanks. Okay. Right, so as said, yeah, I will now discuss the cloud data management and the visualizations for remote manufacturing. And I will start again with this graph that you have seen before. And just give you, now you'll see why we keep reproposing this graph as a thread to help follow along the way we are having these different solutions interact. Yeah. So we have this real time data from the line, and there's this real data, real time access and analysis done locally by IRT, right? So we get this, but then this data from Comunio goes to the cloud data management, where it's then used for the physics-based digital twins by Innova that Manuel just presented, and then it's also used for machine learning algorithms for production defect prediction by IRES, and Sandy is going to present this later. So the cloud data management here is crucial to enable this interactions and this data exchanges to connect the line and the models. Something else that the cloud data platform does is also serve data to user interfaces, to remote user interfaces. Okay, so the box here is called iScan. So before we go into detail more, I just want to take a step back and discuss what iScan is. So iScan is the IES platform for intelligent data management and analysis. And originally, iScan has been developed for use in the built environment to enable the intelligent communities lifecycle. In fact, it is part of the ICL suite of tools by IES, which have been developed to address the needs of buildings, communities, campuses, and so on. So the ICL is a range of digital twin technologies for sustainable and intelligent communities. And here, the use of the word digital twin is indeed the same as those presented earlier by Manuel. However, in our case, it's applied to the physics of the energy and consumption and demand in buildings and communities and so on. So what iScan can do is it can read data from many sources. So it can collate and manage this time series for analysis. It can also collect data, virtual data from forecasting models. And then it has a robust set of analysis and let's say post-processing capabilities inbuilt to prepare and pre-process data for then further analysis and further visualizations. It can be used to then create alerts and alarms. So, for example, if the values are outside some specific conditions, and it's a cloud platform with secure access from multiple users with customizable permissions and so on. So the the sources of data that are in use for ISCAN currently, and in imPURE, of course. So we have the historic data and the real data. So this is what we're getting via Comunio, as Philippe was presenting earlier. Then there's the digital twin data from the simulation, from Innova in this case, and the machine learning data from IRES. So this is just to give you an idea of the kind of data that usually goes through ISCAN. It's really broad, and it is usually data comes from multiple systems in different formats with different governance models, etc. So ISCAN is all about automating the collection of this data from these physical assets and normalizing it and making it all analyzable together. So indeed, this is a very specific theme of the built environment data, but it made it very well suitable for this application on the industrial lines. As such, the amount of data flows to ISCAN as such is really large because of the nature of the different data streams. It can take data in different formats, open formats, your CSV, JSON, SQL, and XML, for example. The connections are many from FTP to there's a dedicated ISCAN robot, which is something that we can deploy to get data. But even email is an option. However, the two that are more relevant for the manufacturing case and the manufacturing context are by far MQTT and the REST API. So and in particular, the API is bidirectional. So it's not to get data in to scan, but also to get data out of scan and have that two-way exchange of data. So in general, how ISCAN is used in manufacturing is, first of all, for data management. So to get that information out of data. So some examples are like to manage multiple lines, multiple data sources, and complex architectures where there's different data sources or maybe different data collection systems that have added on in time, or we can also link to a SCADA if there's existing storage capabilities. The aim is then to be able to visualize the production status securely from a remote location, which was already a relevant use case, but has been even more so during COVID, of course. Then for forecasting, it is to help analyze the whole process, right? So as been mentioned before, this is all about reaching zero defect manufacturing. So having those analytics and data checks on the data based on the logic, on the manufacturing logic that has been identified through the other analysis that by domain experts that have been presented before. So those findings on what are the tolerance levels and what are the conditions that cause an alarm, those can be embedded in ISCAN. So those and part of that analytics can happen in ISCAN, or it can also be done externally by passing the data through an API and run these forecasting models externally. And finally, this is more similar to what Manuel was presenting toward the end. There's this the capability of implementing some predictive control, so support in making decisions and implementing them. So if the forecasting from the digital twins or the machine learning models raise a need to change how the line is being set up or operated, it can be done. This can be done either manually or automatically. So those alarms, those warnings, can be transmitted by ISCAN to the dashboards, or even they can also be sent directly to automated control. So now, we can go back to this slide, understand better why ISCAN is at the center of this graph. But it is this data management solutions that we have created for built environment and expanded to the manufacturing field, or aligned with the imPURE philosophy. It's been repurposed for manufacturing for sure. But then the the novel bit that's been added through imPURE is these user-friendly interfaces for remote manufacturing monitoring, which we call command centers. We are now finalizing the design of these, and I will show you some mock-ups of the features that are going in these command centers. So they're not going to be showing realistic data, but they can be helpful in communicating the key features that they will include. So this is the first live data page, so with the production at a glance. So here we have, for example, we can see the last red value on some key parameters, and then the thresholds or the limits or the target of each parameter. Again, this depending on the optimal design that has been identified previously. We see and we can analyze the last cycle. So and look at the data that's been recorded during the production, and identify if there are values out of limits. Again, even detected by either simple, like this is out of a specific boundary, or by more complex rules that take into account the correlation of the parameters, right? Sorry. And finally, yeah, the alerts at the bottom, this can be based, again, both on this data in iScan, or they can come from outputs of the machine learning models or the digital twin and so on. Then there's, as you can see here, there's this sidebar that divides the various areas of the command center. There's a product page with the target key parameters. So as a bird's eye view of what's in production in the line, and what are the objectives for each of them. And then finally, we have the digital twin page. So this is the one that is going to bring together both that recent history of the key parameters and the digital twin prediction that comes from the Itanova data set, right? And for each of these parameters, the idea is that it's going to be possible to see these key figures. So we have, first of all, at the top, we have this summary. Then for this specific product with the targets, and then for each parameter, we can see this comparison of what's being predicted and what's actually happening in the line. So this is a way to inspect the production as it happens compared to the prediction. It's more to support and validate in continuously whether the design and the settings were appropriate. For each of the parameters, we can see these cards with the prediction, or like the current or live less measurement and minimum maximum temperature. So just kind of a summary view. And these cards here can be color coded. So for example, to signal if the production is aligned with the prediction, or if something's going out of thresholds, and so on. So right now, this is currently under review and discussion in the consortium, but by the end of the project, we will be setting this up for the Basco line. And that's it for me. Thank you for your attention, and feel free to ask any questions. I'm happy to answer them.
Thank you very much, Giulia, for this very informative presentation. Thank you. I saw in the chat there is a question, but I will proceed with the last presentation, and then we will have time to discuss. So I would like now to give the floor to Innovation in Research and Engineering Solution. We have here with us Sandy Bay, which will give us a presentation on defect detection using synthetic data and an exploration of real-time IM cycle data.
Hello, everyone. I hope you can see my screen in full presentation mode.
Not yet, actually. We don't see.
No?
Oh, okay, now yes, but it is double screen. If you can change the
Okay.
display setting. on the top, you can change the display setting by choosing the first option. Swap, yes.
Okay, I think I did it. Can you confirm?
No, we see again in double screen.
Okay.
Maybe you
Apologies for
can.
that.
No, don't worry. Maybe you can try the other display setting because it depends also on your screen mode.
Maybe now?
No.
Okay.
But just try to the display setting, the second option. Let's see if
Yes. Just a second.
yes, don't worry.
I'm having some difficulties.
I'm having a look. If I have your presentation, maybe I can
Yes.
share it if you prefer.
Yes, if you have it, please.
Having a look, I'm not sure. No, I don't have it. If you want to send it to me, or
Okay.
apologize for these minutes of delay.
Yes, apology. Okay, I think I can try one more time. Apologies, everyone.
Okay. Let's see if it works. We see your screen, which is empty.
Okay.
Okay, we see the presentation.
No?
We see it in presentation mode. Perfect. Thank
Finally.
you.
Apologies
Thank you,
for the delay.
Sandy. Don't worry. The floor is
Sorry.
yours.
Thank you, everyone. So apologies for the delay. I'm Sandy Bay, and I'm going to present the last presentation of the webinar, which is the defect detection using synthetic data and exploration of real-time injection molding cycle data. So this presentation was supposed to be done by my colleague George Bacchus, but unfortunately he's not able to attend, so I will present instead. So let's start. This is the outline of my presentation. We'll briefly go through that. First, we will define the digitalization workflow. Then we will explain the pipeline of the data acquisition. In more details, we will talk about the synthetic data that were provided by Innova, the exploratory data analysis that was performed, and lastly, about the output and the tolerances. Next, we will discuss about the machine learning models that we selected and trained with the data. We will explain the outcome of these machine learning models predictions. Then we will talk about the digitalization of the injection molding lines, how we collected the data from ISCAM, and how we developed an automated way to collect the data. Then we will talk about the real-time data and we were provided with the data analytics we performed. And lastly, we will talk about the future objectives, and we'll get into more details about that on the end of my presentation. So let's start with the data acquisition pipeline. So in order to collect the data, we created a pipeline which consists of 4 steps. The first step is to collect the data from the Pasco manufacturing line through iScan with the use of their API. The next step is to explore the data to perform an exploratory data analysis. More specifically, we extracted some distributions of the input data, some correlation analysis in order to define some dependencies between the data. And lastly, we explored the defects, which is the ground truth that can serve as input for the machine learning models we developed. The third step is to clean the data. This means removing any outliers and any possible noise. In our specific analysis, we did not come across any noise, but we included this part in our workflow in case there is some noise. And lastly, we take this processed and clean data and we serve it as input to our machine learning model lifecycle. And this workflow is shown in the figure on the right, as you can see. So as I described, the data from the production line gets stored in the iScan database. We take the data from this database and we perform some analysis, and we then feed this to our model. So because at the time we performed this analysis, we were not provided yet with real-time data, we used some artifact data, which is, these are data simulated by Itainova. I will get more into this in the next slides. So we used this simulation data, which were labeled. This means that we know the output dimensions of the manufactured parts. And with this information, we predicted the probability of a measurement exceeding the signal range. So next, let's move to the injection molding line data acquisition workflow. And as you can see, IRES is on the very right of this workflow. So starting from the left, you can see the injection molding lines from Pasco, and then you can see the sensors that have been installed by University of Strathclyde, which get stored, data from these sensors get stored to the common new device. Then the data from the common new device gets collected by iScan. Then IRES takes the data from iScan through the use of their API, and we collect this data to some local server in our offices. And then we handle the data, we explore the data, and we use them in order to train a supervised machine learning model and predict whether a cycle is defective or not, whether it produces a defective part. So let's move on to the exploration of the data. So as I mentioned earlier, in the time of the analysis, we were not able to have real-time data. So Itainova performed some simulations regarding the injection molding of the oximeter case. And what they did, Itainova, was they selected the most important process parameters and performed a design of experiments in which they varied independently 8 process parameters in defined ranges. And we should know that all combinations were labeled as defective or not. So the parameters, the 8 parameters that were selected, which were the most important, are the following 8. It's the injection time, which is the specified time to fill the cavity at the constant ramp speed. Switch, which is the point at which the machine changes from rad displacement control to pressure control. Packing time, which is the time the packing pressure is kept to compensate the plastic shrinkage during cooling. Packing temperature. Packing pressure, which is the pressure used to pack the material inside the cavity. No, I think I mentioned that. yes, temperature, cooling, movable, which is the temperature of the coolant used to cool the movable half of the mold. Temperature cooling fixed, which is the temperature of the coolant used to cool the fixed side of the mold. And lastly, the temperature cooling core, which is the temperature of the coolant used to cool the sliding core of the oximeter case. So the output that we want to predict is whether cavity is defective or not. We were provided this information by Itainova. And on the right, on the figure on the right, you can see the distributions between all parameters. As you can see, I think the letters are small, but I think you can see we have some linearity correlation. They are fully correlated. Let me zoom in. The temperature cooling core, no, the temperature cooling movable are linearly correlated. So next, let's talk about the output of the simulation. The output of the simulation are per cavity are dimensional parameters and weight parameters. So the weight parameter is the weight of the produced part, and the dimensional are some widths, the flatness, the length about the oximeter cases. And you can see on the right, the figure on the right, the dimension parameters that we used. And so for the limits that were chosen to define if the part is defective or not, for the filling, the part is considered okay if it has been completed successfully. And for the dimensional, the part is considered okay if it is within the defined tolerances. On the table on the bottom, you can see the ranges that each of the parameters has to be in order to be considered nominal. And you can also see the tolerances, the upper tolerance and the lower tolerance. So if one parameter exceeds this tolerance, it means that if at least one of these parameters exceeds tolerance, the whole part is considered to be defective. So next, we performed some correlation analysis for all parameters. As you can see, this is the Pearson correlation for all parameters. One means that they are very highly correlated and dependent. And so the lighter the color, the more dependent they are, and the darker, the least. So as you can see, we can see that the temperature cooling fixed and the temperature cooling movable all are fully dependent. And so we removed one of the two from our analysis because they're fully correlated. We extract all the needed information from the one of the two. We don't need both of them for the analysis. So we moved the temperature cooling movable, and we used all the rest of the parameters. So the next step after we processed and cleaned the data was to select the right machine learned model for our analysis. So in order to select the best model, we have to ask ourselves what kind of problem this is that we want to solve. So we know it is a supervised problem. This means that we have labeled data. So we have the values of all the parameters, and we also have the information of whether the part is defective or not. And also it is a classification problem, which means that we have to classify the data as to classify the data into two classes of whether the part is defective or not defective. These are the two classes. So we used the following four models. I will not get into details about this model. I will just go briefly through them. We used a deep learning model which is called an artificial neural network. We also used the rest of the models were machine learning models. The first one is called random forest classifier, and it is a combination of random forests, which are combined in order to give the best model possible. Next, we use a model called support vector classifier, and lastly, XGBoost, which is again it's the decision tree, which gets improved through training in order to provide the best outcome possible. So in order to evaluate this model, we used some metrics, as you can see on the bottom. These are accuracy, precision, sensitivity, and F1 score. Now, for reference, I will explain the first one, accuracy. So accuracy is defined as the number of correctly predicted outcomes over all the number of our data points. So as you can see on the right on the table, you can see the performance of each model given each one of the selected metrics. So for example, the artificial neural network performed best out of all. As you can see, it has a value of 1 for all metrics. Next to the next model, it was XGBoost, which performed best for all metrics. Then SVC, and lastly, random forest classifier. We should note that the artificial neural network has the best performance out of all, but it was not the one that was selected to use because the data that we had were not a lot. So this is not an indicative value of the prediction performance. So after we trained all of these 4 machine learning models, we can extract some useful information regarding each one of the parameters, of the 8 parameters, and how impactful each one of them were. So we extracted sub value. Sub value is a value that interprets the impact of having a certain value for a given feature in comparison to the prediction we would make if that feature took some baseline value. So what this means is if we see that a feature has a wide range in the figures, the ones on the top have the biggest ranges and the ones on the bottom have the least. If we see that they have a wide range, it means that they are more impactful to our models. And we can see from these figures that the temperature cooling core is the feature that impacts all of our models the most. And the rest vary dependent on the machine learning model. But the temperature cooling core is one that impacts all models the most. Now let's move to permutation importance. After we train the models, we also extracted this information, which is very important because it also gives us an understanding of which feature is the most impactful to the outcome. So let's define permutation importance. Permutation's importance of value 0 means that if the value of a feature is permuted, is changed, the output of the model remains the same. So this means that the model does not change a lot according to the change of this feature. And if the permutations, on the other hand, has the value of 1, this means that the model is dependent of even very small changes of the feature. So as you can see, the temp in cooling movable and the temp in cooling core are the features that, if they are changed, the outcome of our model also changes. So the impact of these features is very important for predicting whether the part is defective or not. The ones on the bold on the figures are the ones that are most impactful. So temp in cooling movable and temp in cooling core according to XGBoost. Temp in cooling core, temp in cooling movable injection time according to random forest classifier. And lastly, about support vector classifier, temp in cooling core, and the switch feature. So let's move on to, again, to the digitalization of the injection molding line. As I described earlier, the raw data from the sensors from the production lines get uploaded to iScan. From there, IRES takes the data through the iScan's Python API. We investigate, analyze the data, make predictions through the machine learning models, and then we use an automated process using cloud services and some other methods, containerized methods, and then we upload the predictions to iScan again, as you can see on the bottom, on the figure on the bottom. And we have automated this process in order to, if new data get uploaded to iScan, we extract the data, it's 3 hours, and we store the predictions to iScan. Okay, so all this analysis I showed earlier was regarding the simulation data provided by the Innova. But on the 15th of February, you had the first Pascal trial run, so we were provided with the first real-time cycle data, and we performed some analysis on this data. There were a total of 139 cycles, and the variables that were monitored were the time, the hydraulic pressure, screw position, and the mold temperatures for cavities 1 and 2, and lastly, the mold pressures for cavities 1 and 2. So these data were not labeled. So given these features, we did not have the information of whether the parts that were produced were defective or not. So we could not train the machine learning models, but we performed some exploratory data analysis regardless. As you can see on the right, these are some samples of the data for all the cycles. On the x-axis, we have the time in milliseconds, and on the z-axis, we have its feature that we are interested in. So hydraulic pressure, mold pressure, and screw position. Now let's move on to the analysis that we performed. Again, we extracted some correlations between all features. As you can see, the temperature mold for each cavity had a pressure correlation of 0.99. Which means that they are very highly correlated. And also the pressures between the two cavities are very highly correlated. And on the right, you can see the distributions for each feature. So as you can see, they are very similar between the two cavities, temperature and pressure, and mean temperature and mean pressure. The only distinctive difference is for the minimum temperature. There is a bit of an offset for cavity 1 to the right, but apart from that, they seem very similar. And next, we performed some analysis taking into consideration the part of the cycle. So this image is provided by IRT, US and Pascal, and it shows the real-time cycle data from the common new device. And it was identified that each cycle can be subcategorized into 4 categories, and these are filling, packing, cooling, and plasticizing. So we perform some analysis for each one of these categories to have a better overview of the data. And let's start with the first part of the cycle, which is the filling part. Here you can see distributions for the maximum and minimum temperature and the maximum and minimum pressure. And the mean on the right. As you can see again, here they are quite similar apart from the the minimum pressure for the two cavities and for the mean pressure for the two cavities. Next, we have the distribution for the features for the packing part of the cycle. Here we can see a more distinctive difference for the distributions regarding the maximum and the minimum temperature, and also for the minimum pressure, and also for the mean temperature for the two cavities. The mean pressure for the two cavities is distributions are mostly identical. Next, for the cooling part, again, we see the distributions. There are some differences regarding the values of the temperatures and the pressure. And lastly, the distributions for the last part of the cycle, the plasticizing. Again, the biggest difference in the distributions can be seen regarding the mean temperature of the two cavities. So that was all about the exploration of the data, real-time data provided by RT. So these are some conclusion and some future work by IRES, and some future steps and objectives are to explore even more data coming from both Pathway and LVES and injection molding lines per cycle data. Also, we would like to acquire labeled data to use this data for the machine learning classifications to improve our machine learning predictions. And lastly, to perform some feature engineering, which means that we would like to investigate if there are further features we would like to include in our analysis in order to extract more information and make better predictions about the effectiveness of the produced parts. And that is all. This is the end of the presentation. Thank you everyone for your attention. And I would be glad to answer any questions that you have. Thank you.
Thank you very much, Sandy. Thank you very much for this very informative presentation. So now we are a bit in delay, but we have a few minutes for any question. I see that there is one in the chat. Maybe, Philippe, you want to raise it by opening your microphone so that we can have a discussion. Also, the participants online can open the microphone if they would like to raise a question to our speakers. So, Philippe,
Yes,
I saw you with the question.
Thanks a lot, and thanks for all the presentations of my colleagues. My questions were more for Manuel, but his very interesting presentation about digital twin. I understand that in your tool you make some simulation, let's say some high fidelity simulation with a good accuracy. Nevertheless, when we make a simulation, a process simulation, there are some assumptions, such as machine is perfect, for instance, but there are over many assumptions. And when you want to use digital twin fed up by real parameters in order to know what happened exactly into the process, there's a sort of discrepancy between the non-perfect process, the real one, and the perfect process, the simulation one. And so my question is how to deal with that. Is there any way to bring some corrections as, something like learning phase in order to to be closer to the reality in the simulation.
Thanks, Philippe, for the question. Yes, you are right. Simulations are simulations. There are many assumptions behind them. So reality and simulation for sure would differ. So there is several ways to do that, type of corrections. The most simple one, that is the one that we have implemented here, is make a correction on the results. So if for a particular combination of process parameters we made a prediction and then the reality shows a different value, we introduce an offset on the simulation results to catch up the difference. Okay, that's the most simple way to do that. There's other ways, perhaps more elaborated. Second way is to look for the correction on the input parameters. So what could be the correction I have to introduce into the input parameters to get the experimental result? Okay, that's a second way.
Okay.
Another way is more elaborated and is more related to the data analysis, data-driven models. It's like a fusion of the digital twins with the data coming from the sensors when creating the model itself.
I understand.
From the very beginning, we are creating the models based on the simulation results. But as the real data is available, this data can be reintroduced on the model fitting, like a training of the machine learning models, but for the continuous models. And that would be the third one. But for sure, the most simple is just to introduce an offset with the difference and then have a look to the tendencies more than the real values.
Okay, thanks a lot for your answer. It's very clear. Thanks a lot.
You're welcome.
Thank you very much. Are there other questions to be raised to our speakers? Also, those that are participating as attendee can open the microphone and pose any question you would like. We also have here our project coordinator, so the National Technical University of Athens. We have Kate Trompeta as representative. And if you have any question, you can open the microphone or write them in the chat. Otherwise, we can close the webinar from today. I would like just remind you with this slide to follow us in our social media. So we are present in 4 social media, and we also have, of course, the project website. We have LinkedIn, Facebook, YouTube, and Twitter. And of course, here you can also see our link to our project website. So in case you would like to reach out for any additional question you may have, just write us and we will be more than happy to reply. And the webinar will be published in our website, and you will have there also our contacts for any question you may have. So I see there are no additional questions, so I think that we can close the webinar. I would like to thank all our speakers and all our attendees to be present today here with us. And we look forward to meet you in our next webinar, which will be in the end of May, the 25th, and it will be related to the supply chain collaboration platform that we are developing within the project. So thank you very much all, and see you soon. Have a nice day.
Thank you. Bye-bye.
Thank you.
Thank you. Goodbye.
Thank you.
Bye.
Thank you all. Bye.
Bye. Bye.